right, hello everyone. We are starting our unit on logs, and this is going to be a pretty long unit, and it's going to be probably some of the most complicated material that we've covered this year. So I want to start off with kind of a brief introduction of logs. We are going to look more at a whole bunch of aspects of logs in the next few weeks. But first, I thought that I would, hopefully this will be recalling of information that you are familiar with already, and try to make some connections before just jumping right in to what a log is. I know you looked at this briefly in Math 3, but not too much, so this will be a lot of new information. Okay, so review though. Exponential expressions. You can't talk about logs unless we talk about exponentials, and you'll see why that is in just a second. But hopefully you guys are aware of how to evaluate exponents, and you know what they mean. If I say 5 to the third power, that of course means 5 times 5 times 5, 3 times. And I hope that you are able to arrive at 125 for that. 2 to the fourth power, again, is 2 times 2 times 2 times 2. And hopefully you're able to see that that is 16. And then of course 10 squared is 10 times 10, which is 100. So I hope you feel comfortable evaluating exponents and you understand the graph of a typical exponential, let's say 2 to the x power. Hopefully you find that somewhat familiar. You know, exponential functions are those kind of amazing functions that rise very, very quickly. You hear a lot about them in real life situations. Perhaps quite recently with COVID numbers and things like that, but you see that they are growing very, very rapidly. So there you have it. That is hopefully a good recap for exponentials for you. All right. The next thing I want to review with you is inverse functions, something that you talked about quite a bit in Math 3. Hopefully you remember this. So inverse functions, if you recall, here's some fast facts about them. The domains, which of course are the x values, and the ranges, the y values, switch when you're talking about a function and its inverse. You may recall doing that in a table. If you think about this example I've given you, f of x is x plus 4. The inverse then would be x minus 4. Okay, so if you think about that set up in a table, if I put my x values and my y values, for f of x, if I put in a -1, I get 3. If I put in a 0, I get 4, and so on. Here's the inverse of that. If I put in a 3, I get -1. If I put in a 4, I get 0. So notice that the x's and y's have switched places in the table, and perhaps you remember that. Another thing about inverses is that if you graph them, their graphs are reflected across the line y equals x, which makes sense since the x's and y's are switching. So over here I have the two graphs, f of x and f inverse of x, and you can kind of see that reflection across the line y equals x, which of course is just this diagonal line that goes through the middle of the graph. So you can see that as well. And then I kind of already talked about this a little bit, but the equations, they, what we say, undo each other, meaning that whatever we do to x in one function is undone to x in the other. So I gave you very, very basic, very simple examples here, but you can see that adding 4 to x and subtracting 4 from x would undo each other. Those are inverse operations, addition and subtraction. Okay, so hopefully those two things right there kind of got you thinking in the right direction. So I'm going to flip this over, and I know this is like a lot of notes. I'm going to put this on the classroom so you can follow along here or print this out or look at it more closely after the video as well. But this is a basic introduction to what a log is. So speaking of inverses, suppose I gave you this exponential function, 10 to the x equals y, and I ask you to find the inverse of it. Well, again, since we just reviewed this, you understand that you're going to switch the x's and the y's. So you might first switch the x's and the y's, and you end up with 10 to the y equals x. But then what? You know your next job is to solve for y to get a new function. But how do you do that when the y is up here? How do you solve for the y? Now, if I take a minute and go back to this example that I gave you on the front page. If I wanted to just take this function and find its inverse, you would recall that f of x is just y. So I would take the function, I would switch the x's and the y's, and then I would solve for y. To get y by itself, I would obviously subtract 4, and so in doing that, I get y alone, I get a brand new function, which of course is our inverse, right? That's how we found inverses in Math 3. Well, so now we're stuck in this situation though of, well, heck, I've got this, I've got y way up here, how am I supposed to get it alone when it's an exponent? So the short answer to your question is that we're going to need to use a whole brand new function called a logarithmic function. Now, in the next few weeks, you're going to have a better understanding of why what I'm about to say occurs. But for now, you're just going to have to take it on faith here and kind of try to understand the relationship now before we get into the logistics of why it works, okay? So what we essentially are doing is taking this operation log of both sides. And yes, it's a word, but it's also an operation. So if I told you to take the square root of both sides of something, you could do that. If I told you to take the sine of both sides of something, you would do that. So this is no different. I'm just asking you to take the log of both sides. It's an operation. If I took the log of both sides of this equation, then this y, this exponent, is allowed to come down front. And ultimately what I would end up with is a new function that looks like this. I'd have my original function here, 10 to the x, and I would have this brand new function here, log base 10 of x is how I say that. The 10 is a subscript. The x is on the same line as the log. This is called the argument, and this is called the base. The 10 is the base. The x here is the argument, so log base 10 of x. So 10 to the x and log base 10 of x are inverses of each other. Now I want to pause here and look at this little star because this is definitely something that you should be aware of. Log base 10 of x is also called the common log because it is so common to have a base 10. You know, our number system is a base 10 system. So it is so common that we actually don't write the little 10, the subscript 10. You probably won't see that anymore. If we're talking about a base 10, we just write it as nothing, log x. If you see log x written somewhere, then that is assumed that it is a log base 10 of x, okay? In your calculators, you want to grab those. In your calculators, you have a log key. That is a log base 10. If you hit let's see, log of 100, that's an example we just saw a second ago. Next example we'll see in a minute. Log of 100, that'll tell you what that is right in the calculator because it knows that you mean for that base to be a 10. Now, if that base is any other number, then you're going to have to do something different in your calculator, and we will look at that in a minute. Okay, so moving on. Log functions can have different bases, just like exponentials can have different bases. So another example here, if you have 2 to the x, you've seen that before, we've graphed that. 2 to the x's inverse would be log base 2 of x. Those would be inverses of each other. Okay, so 2 to the x and log base 2 of x are inverses, so I could do this all day. I could say, what's the inverse of 3 to the x? And again, you recognize that 3 is the base. And so the inverse then would be log base 3 of x. So notice how that 3 again is a subscript and you have the argument x still the same. These are inverses of each other. So perhaps a better way to talk about them would be to call this f of x and to call this f inverse of x. The inverse notation, it looks like a tiny little -1 here as an exponent. Don't say f to the -1. That doesn't make any sense. This is just the notation for f inverse. Whenever you see this, it's just talking about the inverse of the function f. Okay, so again, to recap, we have our log functions, which are inverses of our exponential functions. They kind of look like this every time. You're going to have a base, and you're going to have what you're taking the log of, If you don't see a base here, it is assumed that it is a base 10. So that brings us to our big relationship between logs and exponents. And this is what's going to help you evaluate logs. Now, of course, we can do it in our calculators, and I'll show you that in a minute. But we will, you can also kind of do a lot of these in your head as well. So the big relationship here is that if I have y equals log base a of x, that means the same thing if I rearrange it into an exponential as the base a, notice the bases are the same, little base a, to the y equals x. Okay, so if I ever see a log and I'm like, I do not know how to evaluate that, I can rearrange it into this form to look like an exponential, and I'm going to have a lot better success with that because you guys know a lot about exponential functions. You've had a lot more experience with them. By definition, the base a of a log is always going to be positive, for one thing, and it's not going to equal 1. If the base was 1, think about an exponential function where the base would be 1 when I rearranged it. 1 to any power is 1. That's not going to be a log. That's just going to be a line. So keep that in mind. A is always positive, so you're never going to have a negative base. You can have a fraction, though. You can have a fractional base. You can't have 1, and then you can have anything else besides that. Okay, so here are a couple of logs that you can evaluate without the use of a calculator because you know about exponents. If I was to give you this and say, what is that equal to? Log base 2 of 8. That's how I would say it. Log base 2 of 8. What is that equal to? You would simply use this relationship and you'd rearrange it and say that that means 2. Well, let's say question mark is what this is equal to. We don't know what it's equal to. So if I rearrange it, that means 2 to the, if I'm using this relationship, the y here is the y here, which is the question mark. 2 to the what is equal to the argument. So notice how this, when I rearrange it, x is the argument in the log is what the exponent is equal to. So the argument on the log is what the exponent is equal to. 2 to the question mark equals 8. Well, you know that. You know that that means that the question mark is equal to 3 because 2 to the third power is 8. So your final answer here, log base 2 of 8, is 3. There it is. That's what that's equal to. Now, if you wanted to use a calculator to see that, I don't recommend this because I want you to be able to do these by yourself without a calculator, but I am going to show you. If you go to math, if you go to the math key and you scroll down, you will see log base, it says, at A, log base. If you click on that, again, you guys are so lucky to have these features on your calculator. You are able to just type in, there's the little base, there's the argument, and it'll tell you the same thing that we figured out. So you can do that for things that might be harder to determine on your own. And we'll talk about that too. All right, log of 100, we've already been through this one a couple of times, but notice again, there's no little base here, so you know that it's a 10. 10 to the what is 100, and you know that 10 to the 2 is 100, so this log is equal to 2. Now, what if I was to say log base 2 of 7? Now, that's going to throw you for a little bit of a loop because you think 2 to the what is 7, and you think, I don't know 2 to the what is 7. Who knows? Now, you could estimate what that is because you could say, well, let's see, I know that 2 squared is 4, and I know that 2 cubed is 8, and 7 here falls between 4 and 8. So this must fall somewhere between the two exponents 2 and 3. So I know that it must be between 2 and 3. Could say that, but I don't know exactly what it is. Now again, your calculator could be helpful for that. You could say math, go down to the log base, and you could type that in, 2, 7, and you see that it's about 2.8. Now again, this is certainly a number you're going to have to round. This is not a pretty number, but at least your calculator can help you with that if necessary. Okay, so again, if you're done with this video, what you should be able to do is to understand the relationship between exponentials and logs, hopefully. You're kind of seeing that they are inverses of each other. And then, of course, this big relationship where you can take a log and switch it over into an exponential form to give you a chance to evaluate logs on your own. And in class, we are going to practice this a little bit more. And, like I said, throughout the next few weeks, we'll talk more and more about logs. All right, I'll see you then.